Well, if you recall, we looked at the special case when the surface is given by an equation z equals f of xy. When you can solve for z in terms of the other variables, then there's a relatively easy parameterization. It may not be the most convenient, but you can always use r of xy equals xy f of xy. And I wanted to work through finding the surface area in this case. And by the way, this is valid for some xy in D, where D is the projection of your surface into the xy plane. So let's just work through the details here. We need to find the normal vector. So r partial x is going to be what? Partial x of x is 1. Partial x of y is 0. Partial x of the z component is just f partial x. So far, so good. And then I want to compute r partial y, and I'm going to get 0, 1, and f partial y by the same reasoning. And so now I can compute r partial x cross r partial y. And I'm going to go ahead and let's just see it. So I'm going to get minus f partial x. And then I'm going to get negative f partial y minus 0. So negative f partial y. And then last but not least, I'm just going to get 1. And so the point is, in particular, when you take the length of this guy, I didn't mean to write that, I meant to highlight it. When you take the length of the cross product, you get what? We're going to get a radical, and we're going to get f partial x squared plus f partial y squared plus 1. And in this case, the surface area over f becomes, same formula we saw before, but I just want to realize that the formula becomes the double integral over d of, let's just copy this, of this, the length of this cross product, which we can jump to just this and not have to work it out. So this is a formula that you'll want to have in your back pocket, just so that you don't have to work through the process. You certainly can. It's the same formula. All that I'm putting here is the length of that same normal vector before, but when you know that your surface is defined by z equals f of xy, you can jump right to this equation and save yourself some of the trouble. So let's do an example. So here we're asked to find the surface area of this function, this paraboloid opening up between z equals 2 and z equals 6. And so here's, I get this strip on the paraboloid in the middle, going all the way around, and I want that band. So first off, I need to figure out what am I integrating over. So if you're standing up here, this is you, standing up here looking down, you're going to see this picture. That's what it's going to look like. And so that's the region that we're going to integrate over. Boy, hopefully you're thinking polar right away. That feels very much like a polar kind of problem, and it is. And so we can say, okay, the area here, it's going to be the double integral over d. Let's just write down the formula. We know it's going to be what? F partial x squared. I lost my ability to slide. F partial x squared, f partial y squared plus 1. So this is my f of xy. And so f partial x is just 2x. So I get a 2x squared plus f partial y is 2y. So a 2y squared plus a 1. Let's just put dA to start with over d. So I'm thinking now about how to set this integral up, and boy, I'm going to switch this thing to polar, definitely a polar type region. So what do we have here? We have a 4x squared plus a 4y squared. That's just 4r squared. So this becomes the equals double integral radical 4r squared plus 1 r dr d theta. What's r doing? R is starting at root 2 and going out to root 6. So root 2 to root 6. Theta, you can see, swings all the way around. I don't want to spend too long on this problem, but I thought you might want a tiny bit of help. So first off, let's just realize that, I don't want to record my voice, there's no thetas here in the integrand. So I can immediately separate this integral 0 to 2 pi d theta is just going to kick out of 2 pi. I can jump immediately to 2 pi integral root 2 root x. We'll put the r out front, r 4r squared plus 1 dr d theta. No real problem here, just a u substitution. Do u is 4r squared plus 1. And I'll let you work that out. You're going to get du is 8r dr. And when you make the substitution, you're going to end up with a pi fourths integral 9 to 25 of just root u du. And you should end up with 49 pi thirds. So I'm going to leave the details from this point on down to you. So pause the video, work those out yourselves. And let's just do one more example together, and then we'll call it a lecture. So last example, we want to find the area in this plane that's lying above a certain region in the xy plane. So let's start by graphing the region in the xy plane, bounded by these two equations. So let's start with that, and we'll do this. Or here, whoops, okay. So y equals x squared goes up, x equals square root of y, looks like that. X equals square root of y is the same as y equals square root of x. You just take the positive side of it is what we want. And so that's the region that I'm looking at in the xy plane. I went ahead and graphed this plane for you in Mathematica. So here it is. It's coming out like this. So here's our xy plane, and you can actually see our region here pretty well. So you've got this guy, and you've got this region in the xy plane. And then above that, you're going to get, let's change to like a bright pink, you're going to get a stretched version of that region up here. Does that make sense? It's just the region above that. Maybe mine should be shifted up a little bit. Whoops, I'm having trouble now. Maybe mine should be shifted up a little bit. But there's going to be some image of that in the plane, and it's going to be stretched. It's not going to be equal to this area, but it'll be somehow similar. So we can do that relatively easily because my surface that I want to find the surface area on, I've got uniquely solved for z. So let's not keep writing in pink. Nothing against pink, but a is going to be the double integral over the region in the xy plane, so over d, of the square root of, you compute f partial x and you get 2, so 2 squared is 4. F partial y is 2. 2 squared is 4 plus 1. dA, I like this. This is just 4 and 1 makes 9, so root 9 is 3. So this is exactly 3 times the double integral over the double integral over d of 1 dA. So this is just 3 times the area of this problem. And finding the area of this problem is a Calc 1 problem. You could do that back in Calc 1, and somehow it makes sense, right? The area here is getting stretched, and it's just going to be 3 times whatever this area is. This is a classic double integral. You should be confident in this at this point. You're going to cut it vertically, and you're going to say, okay, y goes from x squared. Actually, you can cut either way. I'm going to cut it vertically. Y goes from x squared to root x. X goes from 0. The intersection is 1. You can check that. That's the intersection point. And you're going to get just a 1 dA here. And again, you can work this out, and you'll come up with that you're going to get 3 times a third, which is 1. So that's the answer here. And you've got everything you need to do the homework from 13.6. We're almost there. We're going to learn how to do surface integrals in 13.7, and then we're going to just see 2 theorems in the last 2 sections. So we're going to make it. Good job. If I can stop the video. Oh boy. Oh, no. Not good.